Hello, my name is Shahriari, and this is a lecture in a series of lectures on introductory linear algebra based on my book, Retrolinear. The object of this lecture is bases and coordinate vectors in vector spaces. So let's review what spanning and linear independence meant in a vector space. These were subjects of earlier videos. V is a vector space, and we have a set S, V1 through Vn, elements of V. So V is a vector space. That means we have addition and scalar multiplication, and they follow the rules of scalar multiplication and addition in a vector space. And we have a finite set of elements in there. Then we say that the span of S is V, or S spans V, if every element of V is a linear combination of elements of S. So a bunch of elements in your vector space that from which you can generate every element of that vector space are a spanning set. That's a set that spans it. If you start with a generic vector space, you might go inside that vector space, find vectors so that linear combinations of them give you every vector. If you can find such a set, you say that the span of that set is your vector space, and that is a spanning set. That set is called linearly independent when the only way to write 0 as a linear combination of them, the vector 0 as a linear combination of them, is if all the scalars are 0. Of course, if all the scalars are 0, and you write the linear combination alpha 1 v1 plus alpha 2 v2 all the way till alpha n vn, you will get 0. There's no surprise there. You have linear independence if that's the only way you can get the 0 vector. If you can find some other way of writing a linear combination of elements of S and get the 0 vector, then they're not linearly independent. They are linearly dependent. Okay. Now that we have that, we can define what a basis for a vector space is. So again, we have a vector space. We have a set S inside V. S is a subset of V. That's this notation means a subset of. Then we say that S is a basis for V if two conditions are satisfied. S is linearly independent and S spans V. The span of S is V. There's one exception to this rule, and that's when V is just the vector space made up of just one vector, the 0 vector. That is a vector space. If you just have one vector and that's your 0 vector, this is a vector space. 0 plus 0 is 0. Any scalar times 0 is 0. It's closed under addition and scalar multiplication, and it satisfies all rules. That is a vector space. But this vector space does not have a basis. And the reason for that is that the only element it has, it's the 0 vector. And the 0 vector, even if it's sitting alone in a set, it's going to be linearly dependent, because you can write a linear combination of this not using the scalar 0 and yet get the 0 vector. So this vector space actually does not have a basis normally, according to our definition. And so what we define, we could just say that it doesn't have a basis, but it makes life a little bit easier in terms of stating theorems later if we say that for this vector space, we have the empty set as its basis. This empty set is the basis of this because we said so, but it doesn't follow the rule that it's a linearly independent a subset that spans V. Okay, before now we give you examples, let's remind you of a couple of things about span and linear independence. So first, about spanning. In a previous lecture, when we talked about spanning, we proved the following theorem. So let's say that V is a vector space over R. That means the scalars are from real numbers. And let's say that you pick a non-empty subset of V. So S is a subset of V, and it's non-empty. There's just a bunch of elements, your favorite elements, that you've gathered in the set S. Then the theorem says that the span of S is a subspace of V. S itself was just a set, but when you find the span, when you find all the linear combinations of elements of S, then you get a vector space, you get a subspace of V. And it, of course, includes S, because every element of S is a linear combination of elements of S. And so span of S is a subspace that contains S. Moreover, if it happens that the guys you picked those favorite vectors that you picked, elements of S, were already sitting inside W, and W was a subspace of V. So the elements of S were in V, but they were also actually inside this smaller, possibly, subspace W. If that's the case, then the span stays within W. If you start with a set of elements S in W, the span of S cannot get out of W. And the reason for that, I mean, we proved this carefully in a previous lecture, but the reasoning is very clear. If you take elements of S and find S, a span of S, you're finding linear combinations. And linear combinations of elements of W are going to be in W because W is a subspace. And if you are in a subspace, when you add things or multiplying by scalars, you stay within. So by those operations, there's no way to get outside of W. And so putting these two things together, one way to say that is to say that the span of S is the smallest subspace of V that contains S. Again, for more on this, I refer you to a previous video. And also, this is actually not really about real numbers. Even if the scalars are something else, and in a previous lecture, we talked about the fact that the scalars don't have to be real numbers, they have to be elements of a field. And the same theorem is true if we have a vector space over a general field as opposed to over R. When we say over something, we're just emphasizing what the scalars are. If this is your first time through linear algebra, just ignore that comment and just think of real numbers as scalars. You won't lose anything. Linear independence, we made the definition, but we had also a characterization of linear dependence in the lecture on linear independence. And this is an important one, so I'm going to repeat it. If V is a vector space, and if you have an ordered set of vectors, so a bunch of vectors in your vector space, and you put them in a particular order, then assume that the first one is not the zero vector. I mean, if you're looking for linearly independent sets, you don't want the zero vector there because the zero vector ruins any set, including just the set by itself is not going to be linearly independent. Then S is linearly dependent if and only if at least one of the vectors of S is a linear combination of the ones before. Okay, so we define linear dependence and independence in a different way, but here we're saying that a set, if we are giving a different characterization. This is if and only if, means that if a set is linearly dependent, this condition is going to be true. And if this condition is true, the set is linearly dependent. So what's the condition? It says that one of the vectors is a linear combination of the ones that come before it in the list. This happens to be a very useful criteria when we are trying to check linear dependence. For the proof of this, I refer you to the previous video. Okay, so let's give you some examples. So the first vector space we're going to look at is Rn, the set of n tuples and addition and scalar multiplication, as we have discussed before in Rn. So the standard basis for this vector space is these vectors E1 through En. Each one of them has only one, and then all the other entries are 0. E1 has a 1 in the first coordinate and then zeros everywhere else. E2 has a 1 in the second coordinate and zeros everywhere else, all the way till En, which has zeros everywhere except for the last coordinate, which is 1. This is called the standard basis for Rn. Now, Rn has many other bases. Just this one, because Rn is a vector space that we work with a lot, and this is one basis that we like a lot and we use a lot, then this has an additional name. It's called the standard basis. As we shall see later in an example, Rn will have many other bases that are not the standard basis. Now, what is this? Why is this the basis according to our definition? Well, the span of this is Rn. Using these vectors, you can get any vector in Rn. In fact, it's very easy to do that. If you want the vector 2, 3, 4, it's 2 times 1, 0, 0 plus 3 times 0, 1, 0 plus 4 times 0, 0, 1. That was the case when n was 3. But any vector in Rn can easily be written as a linear combination of these n vectors. And in fact, I'm telling you how. Alpha 1 through alpha n is alpha 1 times E1 plus alpha 2 times E2 plus alpha n times En. And it's linearly independent because none of the vectors is a linear combination of the ones before. The first one is not the zero vector, and none of them can be written as the linear combination of the ones before, because every one of them, every new one has a 1 in a new place that the ones before all had zeros in that place. And so if no matter what linear combination of those guys you use, you'll still get 0 in that coordinate and you will not get that 1. So this is a basis because of our definition, spans and linearly independent. And as I said, it has an additional name. It's called the standard basis for Rn. So here's R3, and here's a different non-standard basis for Rn. So there are 3 vectors, -1, 2, 0, 2, 0, -1, and 0, -2, 1. And I claim that this is a basis for R3. First of all, this is linearly independent. How do I know that? Again, I use the criteria that I mentioned. Is the first one the 0 vector? No. Is the second one a linear combination of the first one? No, because how am I going to multiply the first one by some scalar and get the second one? For example, that -1 in the third coordinate, there's no way to get that because this guy has a 0 there. Is V3 a linear combination of these two? Well, if it was, then the only way to get this one is from this -1. So I would have to multiply V2 by -1. Well, I could do that, but that I would have to do that. To get this -2, since V2 has a 0 in the second coordinate, I would have to multiply V1 also by -1 to make that -2. But if I multiply V1 by -1 and V2 by -2, then the first coordinate isn't going to work. -1 times -1 is 1. -1 times 2 is -2. 1 minus 2 is -1. It's not 0. So V3 is not a linear combination of V1 and V2, and so B is linearly independent. B also spans R3. Now that's a little bit more complicated to see, but here's one way to see that. I'm going to first tell you that if I add all these 3, and you can easily do that, you get E1. E1 was that first element in the standard basis for R3. If you add them, you get 1, 0, 0. So I don't yet know that span of B, that linear combinations of these elements is all of R3, but I know that I get E1 at least. But also, you can check that I didn't do my arithmetic incorrectly, that E2 and E3 are both linear combinations of V1, V2, and V3 also. E2 was what? 0, 1, 0. E3 is 0, 0, 1, the 3 elements of the standard basis. I can get them as linear combinations of these guys. And intuitively, then if I can get these 3 guys, I can get everything. Because from these, I can, by linear combinations of E1 and E2 and E3, I can get any vector in R3 that I want. And so I first do that. And then instead of E1, E2, and E3, I write what I have here. Now, if I want to say that a little bit more formally, I mean, the basic idea was that just generate the standard basis, and because you know those generate everything, you're good. But if you want to say it more formally, you say that what I just proved is that E1, E2, and E3 are in the span. So this said, but remember, but span of B is a subspace. That was the theorem on span that we had proved. Span of any set is subspace. So span of B, maybe it's not all of V, but it's a subspace. And E1 and E2, E3 are in that subspace. And as we said, when you find the span of a set, it doesn't go outside of that subspace. So a span of E1, E2, and E3 is inside the span of B, is inside R3. But on the other side, on the other hand, we know what span of E1, E2, E3 is all of R3. So span of B is sandwiched between R3 and R3, must be R3. R3 is inside span of B is inside R3, R3 is the span of B. And so B is a basis because B spans and linearly independent. That's the thing you would need to know. Basis means spans and is linearly independent. B is a basis because it has both those properties. Here's some more examples. Polynomials with real coefficients. Polynomials in X with real coefficients, they have also something called the standard basis. And they also have other bases, but the standard basis is 1x, x squared, x cubed forever. This is an infinite set because we're talking of polynomials of any degree. So this is vector space of polynomials, and that's the standard basis for it. Now, if you limit yourselves to polynomials of degree less than or equal to n together with the 0 vector, 0 polynomial, that's called PNR, then the standard basis for that is 1x, x squared, all the way till x to the n. There's n plus 1 elements in this basis. And again, there's other bases, but this particular one is called the standard basis. It's sort of the nicest one. And here's another basis for this time for M23R, the matrices, 2 by 3 matrices with real coefficients. And again, this is called the standard basis, and you can make similar ones for other size matrices. 2 by 3 matrices form a vector space, and their standard basis is the one that has a 1 all the matrices that have 1, 1 in one of the coordinates and zeros everywhere. Zeros everywhere. Again, for each one of these, you have to say, does it span? Is it linearly independent? And the answer is yes. They're linearly independent. For example, the matrices are linearly independent because you can't get any of them from the previous ones because, again, they have a 1 in a place that the other ones only have 0. And they span because it's very easy to write any make 2 by 3 matrix as a linear combination of these 6 matrices. Okay, now I'm going to give you another example. This is really an example of how to use the notion of a basis, but I'm going to say it in terms of a proposition. So because this is a sort of an abstract thing, it's not an example of a particular vector space like the ones before, polynomials, matrices, or R and where. So let's say that you have some vector space and say you have a basis for it, and it has 2 elements, u and v. Then what this then look at this set B, 4u plus 7v and 4u minus 7v. And this theorem says that this guy is going to be a basis for v. Now, this is a little bit of an abstract theorem because I don't know what the vector space is. I don't know what the elements are. I don't know what the addition and scalar multiplication are. I just know that I have a vector space with an addition and a scalar multiplication that follows my rules. And I'm telling you that if in that such a vector space, you happen to have a set of vectors, two vectors, and those 2 vectors form the basis for your vector space, then automatically, without knowing anything about anything, you also know that 4u plus 7v, you can find that, and 4u minus 7v is also a basis. But how would I prove that? And the purpose of this proposition is not so much that this particular result is important for any reason. It's because of the technique, just getting you used to proving things about bases. So again, like any other theorem, when you want to prove things, you first focus on what is it that you want to prove. I want to prove that something is a basis. How do I prove something is a basis in general? I have to prove spanning and linear independence. So I start with spanning. I have to show that B spans. And I'm going to use the same trick I did in one of the previous examples. Instead of showing that B spans everything in V, I will show that it spans the elements of the basis. So I did a little bit of a calculation. I said, like, took it 4u plus 7v and 4u minus 7v and add them. If you add them, you get 8u. So if you divide them by 8 and add them, you actually get u. So u is a linear combination of these 2 new guys, these new guys on the block, and is in the span of B. And similarly, if you subtract these, you're going to get 14v. And so if you divide also by 1/14, you will get a linear combination of these 2 new elements, the elements of B, that's going to give you v. So far, you know that u and v are in the span of B, but then that means that B spans all of V because it's spanning a basis. Why? Because again, if you wanted to say formally, you would say that U and V are in the span of B, but then that means that the span of U and B is going to stay within the span of B because span of B is a subspace, and span of U and V is all of V. So all of V is in the span of B, and the span of B could be bigger than V because elements of B are in V. Okay, so now why is the set linearly independent? So that was an argument. I didn't write down everything about spanning, but I said everything about it. But why are they linearly independent? We've proved spanning. Now we have to prove linear independence. Now we have 2 ways so far of thinking of linear independence. One is the definition, and the other one is any one linear combination of the ones before? The second one is sort of hard to do here because I don't know anything about these vectors. Well, harder to do, not hard to do. But in particular examples, it's actually usually easier to use that. So I'm going to use the definition. So I'm going to say, let's write down some linear combination of these guys equal to the 0 vector. Now you might say, well, would you do that? I thought we were trying to prove linear independence. Yes, we're trying to prove linear independence. We do that by reserving judgment and saying, well, maybe they're linearly dependent. If they are linearly dependent, I should be able to write them a linear combination of m equal to 0 vector. Except, well, of course, I can always do that because I can take alpha and beta equal to 0, but that's cheating. So I'm supposed to be able to, if they're linearly dependent, I'm supposed to be able to do this without cheating and without either alpha or beta or both non-zero. And so if I can show you that alpha and beta have to be 0, then that means that the set is linearly independent. So I write that and then I multiply it out and collect like terms. And I get 4 alpha plus 4 beta times u plus 7 alpha minus 7 beta equals the 0 vector. And now I say, but look, uv, the set S, was a basis. So that was linearly independent. And because that was linearly independent, how is it possible that I wrote some linear combination of those elements equal to 0? I know because they're linearly independent, the only way to do that is to cheat for the scalars to be 0. I can't quite say that alpha and beta are 0, but I can say for alpha plus 4 beta, the coefficient of u, and 7 alpha minus 7 beta, the coefficient of v, must be 0, because the only linear combination of u and v that's 0 is the trivial linear combination when you use zeros. Why? Because u and v are linearly independent because they form a basis. So from that, I get that 4 alpha plus 4 beta equals 0 and 7 alpha minus 7 beta equals 0. You can solve that one way or the other. You could use the method from the 9 chapters or Gauss-Jordan elimination, but that's overkill for this. You can solve this easily and get that alpha and beta must be 0. Because I was able to prove that the only way for this linear combination to be 0, the linear combination of 4u plus 7v and 4u minus 7v, the only way for that linear combination to be 0 is if alpha and beta are 0. I know that this set is linearly independent. And because of that, I know that I've got myself a basis because I've proved spanning and I proved linear independence. Okay, now I'm going to prove another theorem, and this theorem actually is important in the sense that I'm going to use it for something. So let's say W is a vector space. Actually, W could be a subspace of another vector space, but let's say that would just clutter things. So let's just say W is a vector space, and let's say that I have a bunch of elements in W, your favorite elements. Assume that this is a spanning set. So this is a set that spans W. May or may not be linearly independent at this point, but it's a spanning set. Then the following are equivalent. So I'm going to write 2 statements that I'm saying that are equivalent. The first statement is that S is linearly independent. And the second statement is that every vector in W can be written in exactly one way as a linear combination of elements of S. So let's unpack this a little bit. First of all, what does it mean to say the following are equivalent? I'm not claiming that either statement is true or either statement is false. What I'm claiming is that if one of them is true, the other one is true, and if one of them is false, the other one is false. This is the same as saying if and only if. So I'm saying S is linearly independent if and only if every vector in W can be written in exactly one way as a linear combination of elements of S. But because that second statement is too long, writing it as if and only if becomes a little bit confusing and cumbersome because then it's not clear what the 2 statements are, and it's sort of easier to write it as the following are equivalent. So that's that. Secondly, so what am I saying? I'm saying I've got a spanning set. I'm trying to see if it's linearly independent or not. And I'm saying, well, it could be linearly independent, but if it is, then the following fact is true. And if that following fact is true, then it is linearly independent. Now, what is that? It says that every vector in W can be written in exactly one way as a linear combination of elements of S. Now, of course, S spans W, and so every vector can be written as a linear combination of elements of S. So that part is not a surprise, that you can take a vector in W and write it as a linear combination of elements of S. The additional information is that you can do it only in one way. So if you walk in a vector space and you have a set of vectors that span, then that means that if I take a vector, I can write it as a linear combination of that spanning set. But it might be that if I come back after lunch and do it again, I write it in a different way as a linear combination of those elements. No, nothing in spanning says that there's got to be just one way of writing things as a linear combination, writing one element as a linear combination of that spanning set. But what this says is that if that set happens to be linearly independent, then you will only be able to write things in one unique way. If I do it, if you do it, if anybody does it, we'll have to use the exact same scalars because they are just unique. There's just only one of them. Okay, so now we need to prove this. And so because it's an if and only if, we have to prove two things. We have to first assume S is linearly independent, and using that, prove that every vector in W can be written just in one way, not in possibly in two or three ways, as a linear combination of elements of S. Then we ignore what we just proved, and we now assume that we have this uniqueness property that every vector can be written just in one way, and use that to prove that S is linearly independent. So let's get going. So the first direction. So S is a set and the span of S is W. That's given. The first direction, I'm assuming that S is linearly independent. So I know that. And I want to show you. So I'm picking some element W and W. And I want to show you that this guy can be written only in one way as a linear linear combination of elements of S. So how am I going to do that? Well, first of all, I know that the S spans W. So this guy W can be written I'm sure that I can find scalars to write W as a linear combination of these elements. That I know. So what is it that I'm trying to prove? I'm trying to prove that this is the only way that you could write it. And so what's our strategy? Whenever we want to do a proof, you sort of have to have an aim for how I'm going to do that. So my strategy is going to be, you might want to think about how would you structure the proof here. So my strategy is going to be to say that, well, maybe you could write it in some other way. Maybe W could be written as some other way. This is not what I want to prove. I want to prove this is not possible, but let's assume that it was. And I'm not, and then what I'm going to do is that I'm going to try to show you that this was really not that different from the first place. In fact, it was exactly the same as the first way of doing it, in the sense that beta 1 must have been alpha 1, beta 2 must have been alpha 2, and beta n must have been alpha n. If I can prove that, then I've proved to you that W can be written only in one way, because I first wrote it as a linear combination in one way, and then any other way that I write it is exactly the same as the previous one. So now that we have a strategy, we can actually try to do that. So what do we know now? We know W is alpha 1 V1 plus alpha 2 V2 plus alpha n Vn. And we also know that W is beta 1 V1 plus beta 2 V2 plus 3 dots plus beta n Vn. If that's the case, then that means that these two things must be equal to each other because they're both equal to W. Okay, now I can look at this and say, well, what should I do with that? And the answer is, I'm going to bring everything to one side and collect like terms. I can do that because I'm in a vector space. And so what I get is that alpha 1 minus beta 1 times V1 plus alpha 2 minus beta 2 times V2, blah, 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 plus alpha n minus beta n Vn equals the zero vector. So what? Well, I have a linear combination of these vectors equal to the zero vector. Is that a reasonable thing? Well, now I go back to what I know, which is that I'm assuming that S is linearly independent. S is linearly independent, yet I was able to write a linear combination of these elements of S. V1 through Vn is the elements of S. I was able to write them to be equal to the zero vector. So how is that possible? The only way for that to be possible is if I cheated and I use these zeros as scalars. So it must have been that alpha 1 minus beta 1 was 0, alpha 2 minus beta 2 was 0, and alpha n minus beta n was 0. And this means that alpha 1 is beta 1, alpha 2 is beta 2, alpha 3 is beta 3, all the way till alpha n is beta n. I proved what I wanted to prove, which was that a second way of writing W as a linear combination of elements of S was not really different. It was the same as the first one. So I'm done with one direction of the proof. Now I go to the other direction. For the second direction, of course, I can't use anything I did in the first direction because now I don't know that S is linearly independent. I want to prove that S is linearly independent. What I know is that if someone gives me element W in W, I know I can write it as a linear combination of elements of S because S spans W. But what I do know, I know more that there's just one way of writing it as a linear combination of elements of S. Knowing that, I want to prove that S is linearly independent. So again, what's my strategy for that? So how am I going to prove that S is linearly independent? Well, I use the definition of linear independence. I will say, write some, assume that you found some scalars and wrote these guys, and the linear combination was the zero vector. That's supposed to be a no-no unless I'm cheating. So what I want to try to prove is that I am indeed cheating and all the scalars are zero. So that's my strategy. Write a linear combination equal to zero, show that the scalars are zero. This is one of our strategies for showing linear independence. And again, here I'm not really thinking about what I know. I'm just setting the strategy down. What am I trying to prove? S is linearly independent. How do I do that? This is how I do that. Okay. Now, I haven't proved it. I just came up with the strategy. So now the next question is that how am I going to do that? And here you need to have an idea. So, then you need to think about what you know. We know we have this unique representation thing. And we say that, well, we have one way of writing the zero vector as a linear combination of these vectors. But I actually have another way of writing the zero vector as a linear combination of V1 through Vn, which is the cheating way when I use the scalars R0. So, and if you look now, I wrote zero, the vector zero, which is a vector in W. And actually, this should be zero of W, not zero of V, because the vector space is called W. So that's a little typo. So zero of W is written as a linear combination of these. And it's also written as a linear combination of these guys again. But we assume that there's only one way to write every vector, including the zero vector, as a linear combination of elements. So these two must have been the same. And if they're the same, then that means that alpha 1 must have been 0, alpha 2 must have been 0, alpha n must have been 0. So again, representations were supposed to be unique. And so this could not have been a new representation. It was the same as the old representation. So alpha 1 is 0, alpha 2 is 0, and alpha n is 0. And I'm done. My strategy told me that if I proved that, I would be good. So S is linearly independent, and the proof is done. Now, there's a corollary to this. Just repeating what we just did, but in slightly different language. So let's say we have a vector space, and let's say we have a basis. Now, a basis spans, but it's also linearly independent. And now we know that if it is linearly independent, something that spans, if it's linearly independent, then every vector in V can be written uniquely as a linear combination of the vectors in S. So this is a property of bases. So this follows exactly from the previous proposition that if you have a basis, every vector can be written just in one way as a linear combination of elements in that basis. And this allows us to do the following thing. To define something called coordinate vectors. So start with a vector space, find a basis, but order the basis. So ordered basis means that I don't just have a set, but I have a set together with an order. You can decide what the order is, which one is the first element, which one is the second element, which one is the third element, but you want to put them in an order. If I wanted to be really pedantic, I really shouldn't be using the set notation because the set of elements doesn't really have an order. I could use parentheses or something else to show that this is an ordered set, but that sort of clutters things. So I'm just going to say this is an ordered basis for V. Then, what we just said, if you now pick your favorite vector, you can write it as a linear combination of elements. Why can you write it as a linear combination of the basis elements? Well, because basis spans. But why is it unique? Well, because by our proposition, because the basis is linearly independent, these alpha 1 through alpha n are unique. Because they're unique, they are special to V. So as soon as you have V, and write it as a linear combination of V1 through Vn, you have these scalars. Then what we do is that we put these scalars, just the scalars, into a column vector. And we call that the coordinate vector of V with respect to the ordered basis B. So bracket V sub B is going to be, I'm not going to read it like that. I'm going to say the coordinate vector of V with respect to B. This thing I'm going to read as coordinate vector of V with respect to B is alpha 1, alpha 2 through alpha n. And if you have the coordinate vector and you know the basis, you can recreate the element because you can write it as a linear, you know what scalars to use to write it as a linear combination of the basis elements. Okay, so let's look at some examples. So let's say that V is polynomials of degree less than or equal to 3, and of degree less than or equal to 3 with the 0 vector. And let's say that W is this set here that consists of these polynomials. That's some sort of weird looking polynomials. A plus D, that's the constant term, plus 4B plus DX, plus A plus DX squared, plus 7B plus CX cubed. So these are a bunch of polynomials. Okay, so what I'm going to do is I'm going to write down some elements of W. I'm going to let A to be 1 and B and C and D to be 0, and that will give me some element of W. If I do that, I will get 1 plus x squared because A appears in the constant term as a coefficient of x squared, but nowhere else. So I get 1 plus x squared. That's one element. Then I will, and I start a set like that. Then I do the same thing, but this time I'm going to let B be 1, but A, C, and D be 0. And that will give me 4x plus 7x cubed. Then I will let C be 1 and A and B and D to be 0, and I will get just x cubed because C only appears in x cubed. Then I let D be 1 and A, B, C be 0, and I will get 1 plus x squared. And I claim that this set spans W. And the reason is that if you multiply the first one, 1 plus x squared by A, the second one, 4x plus 7x cubed by B, the third one by C, and the last one by D, and add them, so find that linear combination, you will get exactly this general term in W. So in fact, the way I came up with this was designed so that I would get a spanning set by putting one of the parameters equal to 1 and everyone else 0, and repeating that for every parameter. I got 4 elements, and that was the span. And that spans the W. Okay, but I want to find a basis. Is this set linearly independent? And I could try to do that. This is not such a complicated, such a big set. So I could try to figure out if there are any linear dependencies or not. My preferred view is to first rearrange these a little bit, just to make my life a little bit easier. So instead of that order, I'm going to keep 1 plus x squared as the first one, but then I'm going to write the last one, 1 plus x squared, then x cubed, then 4x plus 7x cubed. And I'm going to say, is the first one the 0 vector? And the answer is no, it's not. Okay, I'm going to keep that. Is the second one, 1 plus x squared, a linear combination of the ones before it? No, because there's no way to multiply 1 plus x squared by 5 or 6 or minus 47 or something and get 1 plus x squared. You're never going to get that x. So these two are linearly independent. Can I get x cubed from these? Again, no, because there's no way by multiplying by numbers, by scalars, you're going to get an x cubed out of these. So these three are linearly independent. Well, what about 4x plus 7x cubed? Can I write those as a linear combination of these? And the answer is yes. You would have to do a little bit of work to find out how I got that, although it's not that complicated, because I said, well, if I'm going to get a linear combination, I need 7x cubes for sure. And I need 4 of these because I need 4x. And then I tried to, I don't need, so I get 4x squared. So I don't need the 1 and the x squared. We get 4 plus 4x squared, but putting a minus 4 there gets rid of those. And so I get what I have. So that means that this guy is a linear combination of those. So S is really not linearly independent. But now if I throw away that last one and keep 1 plus x squared, 1 plus x squared, and x cubed, this will be an ordered basis. Why? Because this still spans. Why does it span? Well, because any element of W could write as a linear combination of elements of S. And if you needed to use 4x plus 7x cubed, you can replace that whatever, anytime you needed 4x plus 7x cubed by this linear combination of 1 plus x squared, 1 plus x squared, and x cubed. And so using just 3, you can get everything in W, because using everything in S, you could get everything in W. And this guy is linearly independent because the first one is not the zero vector and none of them is a linear combination of the ones before. Now that I have a basis, I can talk about coordinates. So for example, if you start with the vector 4x plus 7x cubed, its coordinates is going to be -4, 4, and 7 with respect to this basis. Why? Well, because you need -4 of the first one, 4 of the second one, and 7 of the last one to get 4x plus 7x cubed. That's what the coordinate vector means. The coordinate vector are the scalars you need from the basis elements to generate that one element. Now you could also take take that t and rearrange them, change the order. And that would be it would be the same basis, but it would be a different ordered basis. The order would be different. And if you do that, then the coordinate vector will change, because this time you have to say how many of these first one x cubed you need, and I need 7 of those. How many 1 plus x squared I need? I need -4 of those. How many 1 plus x squared I need? I need 4 of them. So this time the coordinate vector will be 7 minus 4, 4. In fact, another basis, another maybe simpler basis for this w is x1 plus x squared x cubed. Why is that? Well, first of all, these guys are in w, because if you look at these last two, 1 plus x squared and 1 plus x squared, and if you subtract them, you get x. And so x1 plus x squared and x cubed, all of them are in w. And using these, you can get everything in b, and so you can get everything in w. Now, with respect to this basis, 4x plus 7x cubed, actually its coordinates is 4, 0, 7, completely different than before. So the coordinates depend on the basis. You have a vector space, you find a basis. Based on that basis, every vector in your vector space will have now a coordinate vector. Okay, so my final example is to give you something very familiar. So let's look at and let's see if this word coordinate corresponds to what we're used to coordinates before. So let's think about R2, which is a vector space that we like. R2 is the plane, the x and y axis. And let's consider the point 2, 4. The point 2, 4, we like to think of it as it's a point in the plane, the point with coordinates 2, 4. That's the way we talk about it. What point is that? Oh, that's the point that whose coordinates are 2 and 4. Okay, now is this use of the word coordinates the same as the one that we introduced in this lecture? The answer is yes, because if you look at 2, 4, you can think of the vector 2, 4, and it was written as a linear combination of the standard basis. 2, 4 is 2 times 1, 0, plus 4 times 0, 1. So we started with the standard basis. We took this element and wrote it as a linear combination of the standard basis, and the coordinates we got were 2 and 4. So 2, 4 is the coordinate vector of the point 2, 4 with respect to the standard basis for R2. So what we really have done is we have taken this notion of coordinates in the plane, or coordinates in the three-dimensional space, and now we have generalized that to arbitrary vector spaces. So we have said, pick any vector space you like, as long as you can find a basis for it, you can have, for every element, you can have coordinate vectors. And as you might imagine, just like coordinates for points in the plane are useful, coordinates are going to be very useful for general vector spaces. So this is the end of this lecture. Keep hydrated, and I will see you in the next lecture.